All right, out there in YouTube world, everybody say hi.
Hi, YouTube.
Oh, I got to turn my computer around so you can hear me. Y'all can hear me. It's like I'm from.
We need a professional mic.
I know, I do have one, but Mr. Kassenheiser had to borrow it back. It's Mr. Kassenheiser's mic for the multimedia class. Like whenever they interview somebody, put on those videos, they mic them up. But you know, they're kind of a little bit more important than these videos, so I guess. So chapter 8 is all about, think about what did we do in chapter 7? Chapter 7 was we learned about exponents, and then the whole second half of chapter 7 was learning how to multiply things together, right? Learning how to multiply polynomials together. Like, for example, what was the method of multiplication if I've got like x plus 4 and x plus 3? What did I do? FOIL, right? It's basically the big distributive property. I'd say first is an x squared, plus outer is a 3x, plus inner is a 4x, plus last 4 times 3 is 12. And then we combined like terms in the middle, right? And said, okay, x plus 4 times x plus 3 would be x squared plus 7x plus 12. That was the end of chapter 7, right? That was like one of the big things that we learned in chapter 7. In chapter 8, we start here and go there. We say, okay, how do we break them apart? That's chapter 8. Okay, how do we break them apart? Maybe you're thinking, well, I multiplied these together, right? What would be the inverse of multiplication? You'd think like, oh, it's probably like division. It's not exactly division. What we're going to be looking at is factoring. Okay, factoring. The process of factoring is a lot like division because we're pulling things out. We're separating things out. Okay. So it's going to be a lot like division, but we're going to call it factoring instead. All of chapter 8 is factoring. We're going to talk a lot about factoring. So what is a factor? Ooh, I got to get guided notes for you guys. Wasn't ready, wasn't prepared. Started the video way too early. Hold on out there in YouTube world. I'll be with you in a second. I'll give you something to think about. Rhode Island, neither a road nor an island.
Oh my gosh, my mind is blown. I knew I was talking earlier about it, Dad.
What was your thing that you were saying earlier? You put a bed in a room, you have less bedroom, but more bedroom. Wow. You paint the outside of a house, it gets bigger. You paint the inside of a room, it gets smaller.
Oh my goodness. Zach, I think you're a genius. But like,
Okay, so, and we're back. So let's think about that word factor. Okay, that word factor. We're gonna start really small here today. Okay, we're gonna start really small. The first thing that we can talk about in terms of factors. Well, let's think about its definition basically. Okay. The whole numbers that are multiplied to find a product are called its factors. Right? If I talked about the factors of, 10. What are the factors of 10? What things multiply together to get 10? Noah. 2 and 5 and 1 and 10. You can say that 1, 2, 5, and 10 are all factors of 10 because you can multiply them together to get 10, right? You don't need to call them pairs or anything like that. You're just taking them as single values. You can say that 2 is indeed a factor of 10. Because if I take 10 and I divide it by 2, I get something even in the end, right? Not even in terms of value. I get a whole number in the end, right? That's what it means to be a factor. Okay? The whole numbers that are multiplied to find a product are called the factors of that product. A number is divisible by any of its factors. Okay? So we can use the factors of a number to write the number as a product. The number 12 can be written in all those various ways. You see it on your guided notes. Those are all different factorizations of 12. I've got 1 times 12, obviously, 2 times 6, 3 times 4, 1 times 4 times 3. But then there's that unique one sitting out there on the end, 2 times 2 times 3. Why is that one unique? Why is that one unique? Think about the number 2. What are the factors of 2? 1 times 2. Anything else? No. What about the factors of 3? 1 times 3. What about the factors of 5? 1 times 5. What about the factors of 7? 1 times 7. What about the factors of 11? 1 times 11, right? Those numbers are unique because they are called prime numbers. Prime numbers. Numbers that only have factors of 1 in themselves. They still have factors. Don't get me wrong. Prime numbers still have factors. They're just itself and 1. Now, again, I go back to this and I say, okay, what's unique about 2 times 2 times 3? That's its what's called prime factorization. Prime factorization. Okay? The order of factors does not change the product, but there is only one example below that cannot be factored further. The circled factorization is called the prime factorization. I'm going to ask you a lot to write out what's called the prime factorization. The prime factorization of any number is getting it all the way down to its prime factors. It's prime numbers that have multiplied together to get that number. Okay? The prime factors can be written in any order, and except for changes in the order, there's only one way to write the prime factorization of a number. Okay? I also can accept powers. Like if you really wanted to, I could say 2 squared times 3, because 2 times 2 is 2 squared. That would be fine as well. 2 squared does represent 2 times 2. Okay? All right. Yeah. Let's get to it. Let's find the prime factorization of 98. The prime factorization of 98. You're going way too far on your own. You're not understanding what we're doing here. Because none of that's right. You need to erase all of that. All right, the prime factorization of each number. What I would do to find the prime factorization is do what's called a factor tree. You guys remember doing factor trees? Let's do a factor tree. What is a factor tree? Well, that basically divides the number into 2 parts using 2 factors. Okay, so what are factors of 98? It's even, so it's divisible by 2, right? So 2 times what is 98? 49. Okay, is 49 prime? No. What is 49? 7 times 7. 7 times 7. Okay, is 2 prime? Yes. Is 7 prime? Yes. Is 7 prime? Yes. So that's what's called its prime factorization. Once we cannot divide it out even anymore, and again, I'm not adding and subtracting here. I can't separate 7 into like 5 and 2, right? I'm talking about multiplication. So this is its prime factorization. 2 times 7 times 7. That's its prime factorization. Again, if you really wanted to, we could say 2 times 7 squared. Okay, let's do the next one. Let's try 40. Let's try 40. Okay, what multiplies together to get 40? What are factors of 40? Noah? 2 and 20. Now, I heard somebody say 10 and 4. You could do that. That's totally fine. Guess what? You'll get the same prime factorization in the end. Factors of 20, 2 and 10. Factors of 10, 2 and 5. So therefore, the prime factorization of 40 is 2 times 2 times 2 times 5. If you wanted to write it this way, 2 to the 3rd times 5, that's just as good. Questions about that? Again, don't think that we're creating some new number here. All I'm doing here is just rewriting the original number. Like if I went back and said 2 times 2 times 2 times 5, guess what we get? 40. I'm just rewriting the number in a different way. Try the last one on your own. 33. People always say this one's prime. It's not prime. What numbers multiply together to get 33? 11 times 3. 3 times 11. Is 3 prime? Is 11 prime? Yes. So the prime factorization is 3 times 11. Okay. You keep going until you get prime factors, until you cannot divide it anymore. All right. Now, factors that are shared by 2 or more numbers are called common factors. You guys remember finding the GCF? Remember that? That is called the greatest common factor. GCF stands for greatest common factor. The greatest of these common factors is called the GCF. Take a look at that. Take a look at the list that we have. I'm finding the factors of 12 and the factors of 32. Look at the list that I've got. 1 times 12, 2 times 6. And people, I don't know who teaches this. Maybe you guys still know this. I heard it a couple years back, somebody calling this the factor rainbows. Did you guys do that? Factor rainbow.
I remember.
The factor rainbow.
Oh my God.
No. I think one of the teachers at Lake teaches that. Mrs. Tobin? Oh,
I still remember winning this thing. At least comment.
Shout out Mrs. Tobin. Way to go. Factor rainbows. All right.
I remember doing this.
Least common denominator. Now the greatest common factor can also be actually that's LCM, that's least common multiple. That's, okay, never mind. I don't want to dive into that. But yeah, I think you were thinking, instead of factors, those are multiples, which is the least common denominator. Anyway. Taking a look at the factors of 32, it's 1 and 32, 2 and 4, 1 and 32, 2 and 16, 4 and 8, right? Now, take a look at the common factors out of each list. 1, 2, and 4. None of the other ones are in both lists. They're only in one of the 2 lists. So you're looking at what is the biggest number that's in both lists. So the greatest common factor out of both lists is 4, right? The GCF is 4. That's the biggest number that they both have in common. Now, ladies and gentlemen, you've been doing this process for a while now, so I'm going to ask that you just go straight to the number 4. If you wanted to write out these lists, could you? Of course. But I'm going to ask that you go straight to the 4. Guys, take a look up here. This is not in your guided notes. This is something that I teach that I think it might be beneficial as well. Think about the prime factorization. Guys, eyes up here. Think about the prime factorization of 12. The prime factorization of 12 is 2 times 2 times 3. You follow me there? Simple. The prime factorization of 32. 2 and 16, 2 and 8, 2 and 4, 2 and 2. So it's 1, 2, 3, 4, 5 2s. 32 is 1, 2, 3, 4, 5 2s. Okay. Common factors. What are the common factors that I see? Don't I see a set of 2s and a set of 2s? Are there any more common factors? No. Those are my only common factors. So guess what my GCF is? 2 and 2. What's that become? 4. So my GCF is 4. So another way to find GCF is by looking at its prime factorization. You take the common factors out of the prime factorization, and that's what gets you your GCF. I'm going to show you that method again using this. I think you guys have used that like factor rainbow thing before, or just like listing out the common factors. That's fine. But I like to use this prime factorization method. But honestly, I would hope that you go straight to the number. Like, can anybody tell me what the GCF of 160 is? What do you think? If you had to guess at it, what do you think, Noah? 20. Okay, 20. Does 100 divided by 20 work? Does 60 divided by 20 work? Yeah, and that's a pretty big number, right? I hope that's the biggest. I should probably test a couple other things, like 60 divided by 30. 30 is big, right? But is 100 divided by 30? No, that doesn't work. So maybe that's it. Maybe 20 is it. Let's check. Prime factorization of 100 is 2 and 50. You'll notice I always like to go by 2s. It's just habit. 2 and 25, and then 5 and 5. So 100, the prime factorization of 100 is 2 times 2 times 5 times 5. Is everybody following me there? Okay, now let's take a look at 60. Okay, that's 2 and 30, 2 and 15, 3 and 5. Is everybody following me there? So the prime factorization of 60 is 2 times 2 times 3 times 5. Okay, now I'm going to highlight common factors. I've got a set of 2's in common, another set of 2's in common, and then I've got a set of 5's in common, right? Everybody following me there? So my GCF is now going to be a set of 2's, a set of 2's, and a set of 5's. What is 2 times 2 times 5? What's 2 times 2? 4. What's 4 times 5? 20. We were right. The GCF is 20. Does that make sense? I'd like you to try that method on the next one. Okay, please try that method on 12 and 16. Now, I bet you could probably guess at what the GCF is in this one. What do you think? 4. Test it out. Do your factor tree method to see if that actually works out. Would I like you to just go straight to 4? Yes. But do this method to see if that actually works still. Okay, so 12 and 16, those prime factorizations are pretty easy. 2 and 6, 2 and 3, 2 and 8, 2 and 4, 2 and 2. So 12 is 2 times 2 times 3. 16 is 2 times 2 times 2 times 2. So my common factors are 2 sets of 2's. So my GCF is 2 2's, which is 4. So yes, indeed, the GCF was 4. Questions about that? Does that make sense? That's how I like to do GCF. Okay, we can also find the GCF of monomials. Ooh, so now we're pulling in stuff from chapter 7. Monomials, fancy word now. Monomials. We can find the GCF of monomials, and guess what? They include variables. Oh, yes. So exciting. To find the GCF of monomials, we write the prime factorization of each coefficient and write all the powers as products. Yep. Ooh, this is fun. Okay, think about the prime factorization of 15. Well, that's an easy one. The prime factorization of 15 is 3 and 5, right? The prime factorization of 9 is 3 and 3. Now, let's list out the prime factorization of each monomial. 15x to the third. Well, isn't that 3 times 5 times x times x times x? Isn't that true? Isn't x to the third just like x times x times x? Because that's what we're doing when we write out prime factorizations, right? We expand it out as a product. And then we have 9x squared. Well, that's just 3 times 3. And then there's 2 x's, right? So what did we do before? Well, we just not combined, but found common factors, right? So what's my GCF? Well, my GCF in this case is a 3, and then how many x's did we have in common? 2, right? Times x, which in other words is just 3x squared. That's my GCF. Let's try another one. 8x squared and 7y to the third. 8x squared and 7y to the third. Okay, well 8 is 2 and 4, and 2 and 2, and 7 is 1 and 7, right? So 8x squared written out is 2 times 2 times 2 times x, and 7y to the third is 7 times 1 times 7, but we wouldn't write it 1 times y times y times y. What do we say about these two things? What's their GCF? The GCF is 1. The GCF is 1. Why is it 1? Because don't all numbers have a common factor of 1? Can't we take 1 times anything? And can't we divide anything by 1? Right? So 1 is a common factor to anything that we want. Even things that are prime. The GCF is just 1. It doesn't have anything in common. Nothing to highlight here. Okay, so the GCF is just 1. Let's try another one. I'll let you go ahead and try this one on your own. Okay, so we now look at my GCF here by looking at the prime factorization of each part. So here is 2 and 6 and 2 and 3. So we'd say 12x is going to be 2 times 2 times 3 times x, right? 28x to the third, well, 2 and 14 and then 2 and 7, right? So it's 2 times 2 times 7 times 3 x's, right? 2 times 2 times 7 times x times x times x. Two times 2 times 7 times x times x times x. Okay, now, not an eraser, highlighter. We want to go, okay, here, common factors, and then one set of x's, right? Anything else they don't share. So that means we get 2 times 2, here's my GCF, 2 times 2 times x, in other words, 4x. Now, how do we get to that point without having to write out these lists? right? Because that's the goal, right? We should get to the point where we don't have to write that out anymore. We can just intuitively know that, okay, the GCF is going to be 4x. Well, think about the numbers, right? You should start by now recognizing GCF of just numbers. The GCF between the 12 and the 28, they're both divisible by 4, and nothing bigger, right? Anything else bigger than 4 that can divide by both of them? No. I can divide 12 by 6, but 28 does not divide by 6. I can divide 28 by 7, but 12 does not divide by 7. So 4 is my biggest value. Now, how do I figure out about the variable? How do I figure out the variable? Does anybody notice the pattern between them? Noah? Yeah, whatever number has the smallest amount. Yeah. Does that ring true for all of them? Yeah. Look, this is 12x to the first, right? The smaller value of x, the smaller exponent on x became the GCF. Is that true for the one that we did before? What was the smaller value, x to the third or x squared? What ended up in my GCF? X squared. Okay. So going straight to your GCF is now a little bit easier with variables. You just find the smaller exponent, and that's what ends up in your GCF, as long as they share it. Smallest exponent in both that they share. So let's try to go straight there. Let's try to do it. What number divides 27 and 45? 9, right? We know 3. Obviously 3 would divide them both. But 9 is a pretty big number. Does anything else, 27, does anything else divide 27? No, not that I can think of, right? Other than 27 itself. Does 45 divide by 27? No. What other numbers divide 45? Well, 15 divides 45, but does 27 divide by 15? No. So it looks like 9 is our number. Okay, now I take the pieces in common. X squared and x to the third. They both have x's, right? So what's my smaller power on x? 2. Do they share any y's? Do they both have y's? No. So that does not get included in our common factors. So our GCF is 9x squared. Okay? If we wanted to go through the work and see it, yes, of course we could do that. 3 times 9 and then 3 times 3. So 27 would be 3 times 3 times 3 times x, right? 45, that would be, oops, I put it in here, would be 5 times 9, which is 3 times 3. So 45 would be 3 times 3 times 5 times x times x times x times y times y. Ugh. And then we have 3x, which is just 9x squared, right? So we should try to get to the point where we don't need the prime factorization anymore. That's the end goal. Is it always there for you to fall back on if you need it? Of course, if you need it, okay? Is there another one? No, that's not. All right. Oh, I love these types of problems. The cafeteria has 18 chocolate milk cartons and 24 regular milk cartons. The cook wants to arrange the cartons with the same number of cartons in each row. The chocolate and regular milk will not be in the same row. How many rows will there be if the cook puts the greatest possible number of cartons in each row? What's it really asking for me right there? I'm really asking for the greatest common. I know we did a whole set of notes on the greatest common factor, and you're like, well, duh, it's going to ask for the greatest common factor. But think about it. I've got 18 chocolate milks, right? What are the possibilities that I could put them into rows? I could put 1 row of 18, right? I could put 2 rows of 9. I could put 3 rows of 6, right? Those are the possibilities. I could put 6 rows of 13, or of 3, right? Think about 24 regular milk cartons. I could put 1 row of 24, 1 row or 2 rows of 12, 3 rows of 8, 4 rows of 6. What am I doing there? What am I listing off for that number? Not multiples. Multiples get bigger. factors, right? I'm listing off its factors. So if I want the biggest row, I want the biggest factor. I want the greatest factor that they both share. They have to have the same number in each row. So they have to be common, right? And I want the biggest common factor. So that's really all I'm going to do. I'm just going to find the greatest common factor of 18 and 24. Now, some of you guys are like, oh, I got it. It's 4. First of all, 18 does not divide by 4. And then you may be like, oh, I got it. It's 9. Because 18 divided by 9 is 2. 9 divided 24. It's got to be a different number. What is it? 6. 6. I'll show the prime factorizations out if we need it. 2 and 12, 2 and 6, 2 and 3. So 18 is 2 times 3 times 3. 24 is 2 times 2 times 2 times 3. So my G, not a crayon, highlighter. My GCF is 2 times 3. Which in other words is 6. Now answer the question that was being asked. How many rows will there be if the cook puts the greatest possible number of cartons in each row? Is 6 the answer? No. 6 is the amount of milk cartons I'm putting in each row. So 18 was it chocolate? 18 chocolate. So 18 chocolate milk. How many rows of chocolate milk are there going to be? If I have 6 in each row? No? 3 rows. If I've got 24 white milk, is it white milk? Well, regular, excuse me, regular. 24, and I have 6 in each row. How many rows are there going to be? 4, right? How many total rows do I have? 7 rows. That's my answer. That's my true answer. See, there are a lot of times when we start getting to reviewing for air test time, you guys do the math for the problem, and then you're like, oh, I got my answer. Put on the answer blank. Done. Move on to the next question. Submit. Like you would have gotten 6 and said, ooh, submit 6. Is 6 the right answer? No. Go back and read the problem. Understand what the problem is asking you. Don't just spit out an answer because you did some math. Go back, take a minute, reread the question, figure out what it's asking you. All right. Everybody say bye to YouTube world.
Bye, YouTube.
Hey, don't forget to subscribe.
So that's